All right, I'll go ahead and start. So this week, we will be talking about, I think this is chapter 2, and it's about describing motion, specifically in one dimension, okay? And we'll basically go to some basic methodologies you learned in high school to describe the motion. So these are the reading assignments. That's very easy to read. I encourage you to do it as soon as possible so that you don't have to, spend time later. And hopefully we can solve these examples tomorrow, right? First, let's start. So what is, I want to introduce some terminology. And for this, I need to introduce you some grammar. And the first thing to talk about is distance versus displacement. So the distance, maybe I can use, is by definition, what is the distance? Maybe I should ask you. It is the total length of the path you travel. Okay. And this should be compared with displacement. And the displacement is after the whatever your motion is, what is your distance? Your how far are you to your starting position? How far are you to start? Okay, these are two things. So the important thing is, I think maybe I can write it here. Distance has, what does it have? It has it's a number, it's a number with unit, which is meter in our case. Whereas the displacement is a number with unit. Anything else?
Direction.
Vector.
Exactly. And the direction. So that's the important keyword. So basically, we are working with vectors when we are talking about displacement. This is like a vector quantity. And we call this one scalar. Okay? It's just some words. Here's the example. Suppose you go 70 meters to east, turn around and go to 30 meters to west. And the question is, what's the total displacement? What's the total distance? Total distance traveled is 70 plus 30, which is 100. Total displacement is this amount because that's the distance you are to the beginning position, which is the displacement. Here is another example, an ant starts, this is I just copied from your book, starts at x is equal to 20 centimeters on a piece of graph paper and walks along x-axis to x is equal to minus 20 centimeters. It then turns around and walks back to x is equal to minus 10 centimeters. What is the ant's displacement and total distance traveled? I think you can probably draw a picture for this. Something like that. This is the x-axis. Let's say this is the 0. And ant is initially at x is equal to 20 centimeters. And it starts here, goes to minus 20, turns around something like that, and travels like 10 centimeters east, right? Yes, and in the final position, let's say they are not to scale, but minus 10 centimeter. The total distance, you can just sum this up. Distance is equal to 20 plus 20 plus 10, which is equal to what? 50 meters. And the displacement is how far is it? It's like, I think, this chunk plus this chunk is equal
meters.
to 30 meters. Thank you. And I think we have to give a direction because it has to have a direction. Maybe if we call this, let's call this like east and west, then it's going to be 30 meters west. Okay, simple stuff. But it doesn't hurt to be careful to begin with, okay? So let's introduce more stuff. Now I want to introduce velocity, and the velocity is, for this, I need to first introduce something called average speed. Speed, which is by definition what? It's like distance traveled take this and divided by total time elapsed. Okay. Again, the speed important thing is like speed is scalar. And now we need to introduce exactly like distance. We have to introduce velocity. And how do we introduce velocity? Velocity is, okay, displacement divided by time elapsed. And this is like what? Let's just formulate this. It's like final position minus initial position, like x2 minus x1. Let's call this final. This is initial. And let's do the same with time. T2 minus T1. Okay. Sometimes we show them with delta x, delta t. And since we are talking about average, this is the definition of average velocity. Okay. And again, just to remind you, velocity is vector. Now I want to introduce this thing called instantaneous velocity. Instantaneous velocity is basically average velocity, but in an infinitesimal time, in a very tiny time interval. Okay, so we show this without v. There is so for averages we generally use v bar. A bar over a quantity means it's the average. No bar means it's instantaneous. And the way we do this is like what? Limit, let's call delta t goes to 0. Did we use delta? Yes. That's the ratio delta x, delta t. What is this thing? Does anybody remember? What's the definition of this thing?
Deriving.
Dx over dt.
Yes, the first derivative, dx dt. Great. Basically, you need to take the derivative of position with respect to time. If you want, you can think of like your position, x of t, a function of time. And when you take the derivative, it's your velocity. So basically, if you are driving, what you see in your speedometer is your speed. If you like, it's your instantaneous speed. And if you look from your window and find out the direction you go along with your speed, that's your velocity. And to get this mathematically, we take the first derivative, and the first derivative is, as you know, the slope of a curve, right? So if you have like a curve like this, x versus t, let's say, and you are following this red line, at any point to find your instantaneous velocity, you need to take the derivative. And the derivative is nothing but the tangent to the curve, the slope. So for this, if you want the derivative here, you just draw the slope. And if you have the function, you can just take the derivative. Or if you are here, this is the slope. If you're here, it's the slope. Somewhere here, it's like a slope, right? Any questions? And I think if you are scared with, I think some people are worried about these things when they see derivatives. Let's just move this a little bit. Yes. Okay, maybe like that. Okay. I think so far the only derivative you need, okay, maybe I can write it in this corner so that you can use it if you want to. So the only derivative you need in this course for a long time, and that's, let's call it d dt or something, and this something is like some constant, let's call it c times t to the n power of t, and that's equal to c times, we are assuming n is bigger than -1, or n is not -1, let's say it's n times t to the n minus 1, okay? If you know just this formula, you'll be in good shape for a long time. All right, let's continue. So we introduce acceleration. So we introduce speed and velocity. Let's do the same thing to the velocity. So I want to introduce average acceleration. The same way we introduce the average speed. So average this is by definition. This is like change in velocity divided by change in time. So let's again call this V2 minus V1 divided by T2 minus T1. This is final velocity, and this is initial velocity. Okay, and again we use bar, and the acceleration is shown with A. We will show this with A bar. If you like, this is going to be equal to what? This is going to be equal to delta V delta T. So something that some people can be confused sometimes is deceleration. What is deceleration?
Negative acceleration.
Right? So it's basically acceleration, exactly the same thing. But if the speed is decreasing, people sometimes call this deceleration. I mean, speed is decreasing. An object decelerating means its speed is decreasing. There is like some acceleration, that's it. Okay. Now I want to introduce the instantaneous acceleration. What is it? It is, let's show it with A. It is exactly like velocity. It's average acceleration in an infinitesimal time. Right? It's like limit delta t goes to 0, delta v, delta t. But again, this is the mathematical definition of derivative. of, so this is the derivative of v with respect to t. This is the derivative of v with respect to t, but we just obtained v as a derivative of position. So this is derivative of derivative is second derivative. So this is d square x over dt. So in the previous case, we had x versus t. Now we have v versus t. Like, be careful, this was x versus t. And if you have v versus t, that green line, the velocity function, and the slope of this velocity function at any point is your acceleration, because it's the derivative. Okay. So for slope, I think if you have this green line, so if you want to find the average acceleration between t1 and t2, you basically take these 2 points and look at this triangle. And the tangent of this triangle is this side divided by this side. That's exactly what we introduce here. And if you take the limit in which this P2 moves infinitely close to this P1, that's this slope line, and that's the derivative here. Any questions or comments? Maybe we can just solve an example to see how this works. Here's again an example from the book. Acceleration is given x of t. A particle is moving in a straight line so that its position is given by the relation x is equal to 2.1 t squared plus 2.8 as in example 2.3. Calculate A is average acceleration during the time interval from t1 to t2, and it's instantaneous acceleration as a function of time. I think so for average, what do we need? It's asking for A bar, V2 minus V1 divided by T2 minus T1, right? But we know what these things are. This is like 2.1 times 5.0 squared plus 2.8 minus again 2.1 times 3.0 squared minus 2.8, and divide this whole thing by T2 minus T1, which is 2.0. And if you do this calculation, what is it? Okay, let me try to pull my calculator. Yes, you're absolutely right. What I calculated is V bar, right? Is this what you mean? And this is meter per second. The question is not asking, but that's fine. So the average acceleration is like, I need to calculate the velocity at these 2 points. Velocity is the derivative, and it's going to be 2.1 times 2 times t, and the other one is constant. So A bar is going to be equal to 4.1 T2 minus T1. T2 minus T1 is what? 3, okay, 5 minus 3 is like 2.0, and I divide this by 2.0, this is equal to 4.1. Is this correct? How about this one?
Yes, it is better.
Yes, thank you. And if you calculate the, okay, this is asking for average acceleration during time interval, blah, blah. Instantaneous acceleration is basically the derivative, second derivative. And so this one was A bar, this is A, dV, dt, and this is equal to, just take one more derivative, which is going to be constant, so that's 4.1 meter per second squared. Okay. And as a bonus, you get the average velocity because I wasn't careful with the question. How come we don't find the derivative of x with respect to t first? I actually did. Good job, right? A lot of questions. That's good. Let's continue. Now let's come to this point, like motion at constant acceleration. So what this means is, okay, let me try to pick up my pen. So the acceleration does not change with time. So if that's the case, you will see there will be a lot of simplifications of equations. Simplified set of equations, which we'll drive in a little bit. And this simplification is actually important because there's actually a very common case, like motion you see around yourself, like projectile motion on Earth, like, for example, e.g. free fall, projectile motion. These are all at constant acceleration. So it's actually a good exercise to try to get some grasp of this thing, okay? So the punchline is A of t is constant, does not change with time. So the first formula, let's write it like this. 1, if your acceleration is constant, v of t is equal to some initial v, which is v0, and a times t, right? That's the first thing. So I remind you, this is the velocity at time t. This is your initial velocity. This a, which is constant, if it was changing with time, we wouldn't be writing this like this. And t is the total time, okay? For the second equation, let's write this. X of t I think you can write this from high school. This is like your initial x plus your v0 times t, your initial velocity times t, plus now this 1/2 times a times t squared. Okay, third equation. So v bar, what was v bar? It was x2 minus x1 divided by t2 minus t1. And you can think of your velocity versus, okay, I'll write what this is equal to. You can think of your velocity, something like that. So this is v, this is t. If you are talking about constant acceleration, this must have like a constant slope. Otherwise, it wouldn't be constant acceleration. It's like something like t naught. Let's call this one t final. At t naught, you have some v naught. At t final, you have some v, which is this v. That basically, you can take the average, right? You know this is basically take This is going to be equal to V naught plus V divided by 2. Now the final equation for 4, I will derive this, but I am going to use these two equations, this one and this one. So I think we can eliminate time from this and put it in this, right? Let's try to do this and see what happens. Time is equal to V minus V naught divided by A, which is constant. And I plug this in X. X is equal to X naught plus V naught times V minus V naught divided by A. And the last one is 1/2 times A times V minus V naught square divided by A squared. So this A cancels with this A. Now I have the same thing, right? Here V naught V times V minus V naught over A, and I have V minus V naught over A. So, and I can basically manipulate these like this. X, oops, let me pick a better color. X minus X naught should be equal to V minus V naught parenthesis, and open this guy. I have what? V naught plus 1/2 V minus V naught. But I think we can simplify that as 1/2. Okay, this thing is equal to 1/2. Just open the parentheses. This is going to be 1/2 V minus V naught. And I think this one should be plus. Okay, this one is plus. And finally, okay, we got it. This is 1/2 V square minus V naught square. Then basically equation number 3 is, no, equation number 4 is, I think you probably already know this. V square is equal to V0 square plus, I think I also need to put A here, 2AX minus X naught, okay? So if you forget this equation, that's how you derive it, right? That's how you get this. You just eliminate T and plug it in here, and you have an equation purely in terms of V, A, and X. There is no time. And all of these equations we derived when the acceleration is totally frozen. It's not changing with time. So let me just read this question. So this is example 2.9 from your book. You are designing an airport for small planes. One kind of airplane that might use this airfield must reach its speed before takeoff at least 27.8 meters per second and can accelerate at most 2.00 meters per second squared. And the question is, if the runway is 150 meters long, can this airplane reach the required speed for takeoff? Okay. So basically, this problem gives us two things. Acceleration is given. It's like 2.00 meters per second, in nice units. and the distance is how much? Let's call delta x, if you like, is equal to 150 meters. This is the length of runaway. Okay. And the question is, can it reach the speed, which is, let's call this V target is equal to 27.8 meter per second. So A, let's start with A, I think, and exactly like you said in the Zoom, I'm supposed to use this equation, yes. And let's do that. For that, let me first write it. V squared is equal to, exactly like you said, V squared plus 2 times A times, let's say, delta A, delta X. Okay, so we have all of these. So then, and this V naught is 0 because the plane starts from rest. And this should be equal to 2 times A times delta X. And if we put the numbers, it's like 2 times A is 2.00 and X is 150 meters. This is what, 600? And that means we just take the square root. Let me take the square root of 600. Clear 600. How do I take the square root in this calculator? This one. Okay, 24.5. 24.5 meter per second. And I can already tell this is less than the target. So the answer is plane cannot take off. Okay, there will be a catastrophe if you force it. So B, if not, what minimum length must runaway have? Okay, we are going to use the same formula, like V squared is equal to, should we continue? I think I have a little bit more material to go. Let's talk about free fall. So basically, free falling objects are like an example to like motion at constant acceleration. This is motion at constant acceleration. And I think the first observation of these motions was due to Galileo, which actually formed the starting point of like modern physics, right? I think it was first Galileo talking about dropping objects. I think he dropped objects from the tower Pisa, and then he observed that actually independent of their mass, they reach the same time. And he was like curious about how could that be? And then he formulated the motion at constant acceleration. And then later it turned out to be like maybe one of the biggest things in the history of physics, even though it's simple. And Newton came up with his laws, and then we'll learn all this stuff later, hopefully. And so the idea is, so depending on the location, let's say at a given location on Earth or on any planet, as a matter of fact, and we are, of course, considering without, or maybe I can ignoring air resistance, right? We ignore this fact because we know there is air and it affects the speed of objects. And if these are the assumptions, all objects fall with the same constant acceleration, right? Fall with constant acceleration. Okay. And this was due to Galileo. So this constant acceleration is special. So the constant acceleration has a special name. It's called, we show it with G. And I think for many examples in physics, we can just calculate with taking G is equal to 9.8 meter per second square. Okay. And a couple of things I need to note here. First, G depends on your location. Like basically G here is, G in Ankara is different from the G in, like, say, Italy, or like G in the, I don't know, in like in the US, right? So it depends on elevation from Earth. Basically, even at a given location, I think for a good approximation is constant. But if you are talking about like space shuttles, as they go up, if you go up like hundreds of kilometers up in the sky, the G you experience will change as you go further away from Earth. So that's what it means. And finally, okay, what is this? Things like air resistance actually affect this. Basically, if there is an air resistance, you reach a terminal velocity and your acceleration is 0, but we don't consider that case, at least for the moment. So the upshot is, like, generally these are small and we will neglect all of these.
Sure.
Actually, this gravity thing can be really complicated, and the list goes on and on and on. And there are other complications, which I find actually very interesting. Okay. For example, you can check another effect is, like, it can be so complex. So one effect, for example, I'm just pointing this out because I think it's interesting, like many other things. Like, for example, you can check your Wikipedia tidal effect, right? And why do we have like low and high tides? Maybe not as much in Turkey, but in some countries, that's such a dramatic thing. It affects the entire life. So they have to adjust accordingly. And that is actually the gravitational effect of moon on Earth, or basically on ocean. Okay. So this constant G is actually a complicated story, and there's a lot of physics to understand these little corrections to this G. And I think you can read your book for further details. I think it's pretty interesting, and you can actually look at the Wikipedia too if you are interested. Okay. And maybe I can make a couple of more remarks. So in problems including like free fall, I will try to use, for distance, for distance, I will try to use y because it's the height rather than x, okay, this one, rather than x, to point out that's like a horizontal displacement, okay? Like, because this is like a, if you like, vertical motion. But sometimes I may forget that, and I can use, like, say, I can use h sometimes. And also, like, this G, like, I think in aviation, so any acceleration you have is like compared with this G, right? Any acceleration is compared. So any acceleration is compared to G. Like, I think if you are thinking about fighter jets, they are talking about 5G or 10G, things like this. That means that's the amount of acceleration they experience when they fly, when they do these maneuvers, okay? I think that's pretty much it. And I think the formulation is like, I think exactly what we gave in the previous page, X and V and A, you just replace A with G and you do the calculations. Okay. So if you don't have any other comments, I think that's it for me. I'll see you guys tomorrow.